So next we'll focus on generics, which is chapter 11. Uh, so we already use things like array list, string, array list, integer. So let's talk about why we use them in the first place. So generics exist for type safety. They let the compiler check that you are only storing the right kind of object in a list or collection. So without generics, you would be stuck in with raw types like just array list, which basically says I can hold anything. That leads to uh, messy casting and potential runtime crashes. So with array list player or array list enemy, the compiler can warn you if you accidentally uh, stick a like something like weapon in there. So another thing to know is that generics are compile time feature. So at runtime, Java erases the generic information. So the JVM, Java Virtual Machine, doesn't really know the difference between an array list string and a array list integer. So for now, just remember they keep you safe at compile time, but don't exist at runtime. So let's discuss sorting with generics, specifically the comparable interface. So if you want to sort a list of your own objects, like a list of player statistics or leaderboard of score entry, Java needs to know how to compare them. So that's where comparability comes in. It's an interface with just one method, which is so uh, it's an interface with one method that is int compare to t other. So yeah, this is the method. When your class implements comparable, you define how one object should be ordered compared to another. So let's say we have a student class. If you want to sort students by GPA, then you break ties by name. We might write something like override public and compare to student other. And one like this. Uh, an integer GPA com compare is equal to double compare other dot GPA, this dot GPA. uh, so higher GPA first here. Let me put it in the comments. Higher GPA first. Select zoom out. Yeah, that's good. If uh, GPA compare uh, not equal to 0, return GPA compare. And then return this dot name dot compare to other dot name. So this is a tiebreaker. Uh, so here there are a couple of things that you want to notice here. We used where is double dot compare instead of this dot GPA like other.gpa. So that's important because subtracting can lead to so instead of this.gpa minus other.gpa, we use double.compare. That's important because subtracting can lead to weird overflow bugs, and we made sure it's consistent with equals. So if two students are considered equal, uh, compared to should return 0. uh, so now how do we use this? So once your class implements comparable student, you can just call collections dot sort student list, and Java will automatically use your compare to method uh, under the hood. And you can also call student list dot sort null, which is the same thing. So why does consistency matter? Think about using a sorted data structure like a leaderboard or a tree set. So if you're compared to, says two objects are different, but your equals says they are the same, collections can get confused. You might see duplicates when you don't expect them, or lose items. And one more thing to remember is Java built-in sort is stable, meaning if two objects compare as equal, it keeps their original order. So that's useful when you sort by GPA, and then later by name, and the ties maintain order. So here generics give you type safety and clean code to sort to your own objects. Use implement comparable t, uh, this one, and always use helpers like integer dot compare or double dot compare instead of raw subtraction. And keep compare to and equals in sync. So once you got this down, you can sort any array list of your own classes, students, scoreboards, and be confident. You can be confident the ordering works exactly how you want. So that's the skill you'll need for this week's labs activities. um, so that's about it. Next is we'll move to generic methods. So we have already seen generics on classes like array list, string, array list, integer, but methods can also have their own type parameters that gives us a lot of flexibility. So here's the idea. A generic method declares its type parameter right before the return type. For example, public static uh, t t pick ta comma tb, then we return a not equals to is equal to null a b. So here the this t before the return type says this method works with any type t. So if I call pick hello world, t becomes string. If I call pick 10 comma 20, t becomes integer. The compiler infers the type from what you pass in. Most of the time you don't even need to spell it out, the compiler just knows. So let's look some other example which you'd actually use. Static void let me change this to void swap list t again list int I int j let's change this to t temp list dot get I and list dot set I list dot again get this is gonna be j and in list dot set j comma temp. So what's happening here, uh, notice how t can be anything, a list of student, a list of enemy, like if you're working on game development, but or a list of integers. The method doesn't care, it just works. um, and so a couple of things to remember here is, don't use raw types. If you write just list instead of list t, the compiler can't check for type safety, and you'll be back to unsafe cache. And also remember that generics don't work with primitives. You can't have list int. Instead, you use wrapper types like integer. Auto boxing usually handles the conversion between int and integer, but don't assume it works in every generic context. You'll still need list integer, not list int. So yeah, generic methods declare t before the return type. The compiler usually infers the type automatically from your arguments, and they make great utility helpers like swap, first or default, print all, things like that. And just remember to use parameterized types and know that primitives have to be wrapped. Uh, if you get comfortable writing these little generic helpers, you'll find yourself reusing code more often without cache, and with way fewer bugs. That's about methods. Next we have, let's take the generic methods up a notch and talk about type bounds. So up to now, our generic methods worked with literally any type, but sometimes you don't want anything. Sometimes you need to make sure the type has certain abilities. That's where bounds come in. For example, say you want to write a method that figures out the minimum of two objects. You need those objects to be comparable. So otherwise, Java has no clue how to decide which one is smaller. So we add a bound. Uh, let's look at an example. Uh, t extends comparable. Uh, t min ta comma tb, uh, and then we return a dot compare to b, um, equal to 0, a. So t extends comparability. This line tells the compiler this only works for types that know how to compare themselves. Now you can call min on two integers, two strings. It could be two strings, two scores, or even your own player class if it implements comparable player. Uh, so that's one example. Let's look at another example with numbers. Extends numbers. Uh, let's do double sum and list t nums. Now let's take a double total. Total is equals to 0, and let's write a for loop t and nums. Now total is equal to total plus is equal to n dot double value, and then let's close, then return total. So you'll notice that what you had to do is, even though t extends numbers, I can't just write total plus is equal to n, because Java doesn't let's let you use plus directly on generic types. Instead, we call n dot double value. That's why the bound matters. It guarantees these methods exist. So sometimes you need multiple methods. Multiple bounds. Imagine a top performer method that finds the best player. The the player type must be a person and comparable. So we write extends person uh, and comparable, and next we have this t top performer test t people t best is equal to people dot get, and next we have for loop for t people, then if statement t dot compare to best, uh, then 0. Okay, next we return best. So the syntax is always class first, then interfaces. So uh, extends person and comparable t is valid, but you can't flip them. So you might uh, you might hear about wildcards like question extends t or question mark super t. That's related but different. Wildcards control what you pass in. For now, we're focusing on type parameters with bounds, because those give us the methods we need inside the generic. So things to remember here: uh, okay. uh, so don't write t extends comparable without the type argument. That's a raw type. uh, and it'll all use warnings or bugs. Always do t extends comparable t. Don't assume that number magically gives you operators. You still have to call methods like int value, double value. So the big picture is this: bound let you write smarter generic methods. They let you say this method only works for types that can compare themselves, or only for numbers, or only for things that are both a person and comparable. That's why you unlock the exact methods you need without casting. So if you can explain why you choose a bound, like I need compare to, or I needed double value, then you're in the right place. That's exactly what you'll need in this week's labs and other activities. Next is generic classes. So uh, let's keep building on generics. We'll talk about generic classes. So far we have seen generic methods where you add t just for that method, but sometimes you want the entire class to be generic, meaning the class works with whatever type you give it. That's where generic classes come in. The simplest example is a box. Imagine we want a class that just holds one thing. Um, um, let's go back. So private t value. Actually, let's create a class first. Class box t box box, and next we have a public box and t value. This dot value equals value, then close it. And next is public p get uh, return value public void set p value, and this dot value equals value, and then you overwrite. We have public string toString return box. Here we return the value. Yeah. Okay, so when we create it, we decide what type of box holds. Where is it? Like a box string, or box integer, box student, it could be anything. So the type parameter flows through the whole class, uh, constructor, fields, methods, so we can safely store and retrieve value without casting. I'm not going to go details into the syntax. You'll get a better understanding once you do the labs and activities. Even if I go through it, you'll not have a complete picture. So yeah, a quick note on static context. Static methods and static fields don't use the class's type parameter because they exist before any object is created. So if you want a static method to be generic, it needs to be its own type parameter, like u, something like this. Um and Another really useful pattern is something like result t. Um, it's where you want to return when where you want to return either a success with a value or an error with a message. Instead of throwing exceptions everywhere, you can wrap the uh, outcome in a generic class. That's what you'll see in a lot of modern libraries. uh, Things to remember here is, don't mix raw and parameterized uses of the same class. If you write just box instead of box t, you lose type safety and go back to unchecked caches. Be careful not to leak multiple internals. For example, if your generic class stores a list t, don't just hand it out directly. Return a copy or unmodifiable view, so outside code can't break your invariants. So generic classes lets you design flexible containers like box t, result t. It could be anything that can work with any type. You'll use these patterns in your labs to design small reusable generic classes, and the benefit is you won't need cached and your code stays clean and type safe. And the last topic for generics is generic classes with type bonds. So far we have built generic classes like box t that can hold anything. That's flexible, but sometimes you want to put limits on what type t can be. Why? Because you want to guarantee that whatever goes into your class has certain capabilities. That's what type bounds give you. So an example is a sorted box. uh, so imagine a container that always needs to know the minimum and maximum of the items inside. That only makes sense if the items are comparable. So instead of saying class sorted box t, we write something like class sorted box t extends comparable. uh, and let's close this. We have a private list t items equal new array list, and then public void add t item, and close it, and items dot add item, and then close. uh, that's public void. Next we have a public uh, t minimum. Now we return collections minimum items, and then we close it. We have again public t max. We return collections dot max. items, uh, and then we close it. So uh, so the t extends comparable means this class only works with types that implement comparable. Uh, Thanks to that, we can safely call collections.min, collections.max without any cached or unsafe assumptions. Yeah, it's a basic example. It's just finding minimum and maximum items in the box. Uh, so next we have so you, another assumption, another example could be a common pattern. A repository. Suppose you want a generic repository to store objects by ID. That only works if every object can tell us its own ID. For that, you create a identifiable interface first, and then um, you write your repository, similar to what we did with the before example. um, Few things to remember is don't write t extends comparable without the uh, like the actual. Let's write this, it's better to, yeah, don't write t extends comparable without the uh, this one, the t, that's a raw type, and it breaks type safety. Always write t extends comparable t. And don't overstrain your bounds. If your class only needs comparable, don't also tack on unnecessary interfaces. That's more constraints. The more constraints you add, the less reusable your class becomes. So bounded generic classes let you design APIs that are flexible but still safe and meaningful. You're saying the container works with anything as long as the thing supports the behavior I need. uh, yeah, in the labs you'll practice declaring these kinds of classes, adding the right bounds, and then being able to explain uh, in uh, in plain English why the bound is here. For example, uh, I use t extends comparable t because I need to compare extents to find the minimum and maximum. If you can do that, you'll be in a good shape for building generic classes that feel both powerful and safe. That's all for this topic.